The second talk is on finite choice logic programming, and all three speakers are going to be presenting.
So hi, I'm datalog. I like representing things in logic.
Hi, I'm Boolean satisfiability. I also like representing things in logic.
I bet you can help me with a problem that I've been having. So I'm making a little adventure game that takes place on a tile grid, and I want to use logic to describe and then generate grids for the game. So each tile has one of three types, and there's also a constraint that I don't want oceans to be right next to mountains. Finally, I want to calculate all the regions that are reachable from a home region through the forest.
Well, I know how to do two of those things. So for representing the possibility space, I can say every region is either a mountain or a forest or an ocean, and isn't at least two of those things. So that means there's exactly one terrain type per region. And as for the constraint, I can say that if a region is next to an ocean, then it's either a forest or an ocean, so it can't be a mountain. But I don't know how to calculate reachability.
No problem. I've actually got that part. So I can describe reachability in datalog with just two rules. The first rule forces the home region to be marked as reachable, and the second rule forces me to mark each transitively reachable region. Once I can't derive any more facts, I conclude that every other region is not reachable. And I know rules in datalog correspond to propositions in logic, so I should be able to replace comma with and, flip the implication around, and send this to a SAT solver, right?
You certainly can send it to a SAT solver, and your intended solution does satisfy that proposition. Unfortunately, so do many other things. This if-then forces some reachability facts to be true, but it doesn't force any of them to be false. So as a SAT solver, I can freely choose to make any or all of them reachable. You might think you could fix this by turning the if-then into an if and only if. This is called the Clark completion of the program. Unfortunately, this still doesn't work. It forces every reachable region to be next to a reachable forest. But if you look at this example on the right, you'll see there's two forests, which we don't want to be reachable, which are next to one another. Now, if one of them is reachable, all of our if and only if conditions for the other one are satisfied. So we can assign both of them to be reachable, and this still satisfies our proposition. And this is a kind of general problem with SAT. It's not really equipped to define inductive properties like reachability or transitive closure.
So this is a bummer. Like, I can represent half my problem in logic according to a SAT solver, and I can represent half of my problem in logic according to datalog, but I can't represent the whole problem with logic all at once. If only there was some hero who could help us.
Oh, hi. Hi, datalog. Hi, Boolean satisfiability. I'm finite choice logic programming. And I think I might actually be able to resolve your tensions. So datalog, something I've always liked about you is that you have a very high standard of evidence. So you'll only accept that something is true if there's some kind of justification for it, right? But on the other hand, something I've always admired about you, Boolean satisfiability, is that you've got a very open mind. You'll accept many possible explanations for the evidence that you see, whereas datalog really only accepts sort of one canonical version of the events. So let's see what we can do about this, right? So I want to start kind of with a fresh slate, and we'll move away from this black and white Boolean mindset. And instead of having a predicate like forest of home that can have the value true or false, we're going to introduce something called an attribute, terrain of home, which can have the value mountain, forest, or ocean. And we'll write this as the terrain of region is forest, where the is here is just syntax. But critically, what we want is that each attribute, so in this example, the terrain of each region, can only ever have one value at a time.
So that's actually totally reasonable from a datalog perspective. What you're saying is that terrain is a two-place relation with a functional dependency from the first argument, the region, to the second argument, the terrain type. That's actually pretty common in datalogs to have functional dependencies.
Cool. So if we make this change, we can return to our original spec and start writing this program. So for the reachability constraint, we can basically use the old datalog program. We just need to tweak the syntax as we described before. But for the next step, prepare yourself to enter the unknown. So in finite choice logic programming, we can represent the second constraint with a rule that looks like this third line of code here. So for any region R, there's a free choice between the region having mountains, forests, or oceans as their terrain. This rule forces each region to have some terrain type, and it requires that it's one of the three that we expect. So then finally, for the constraint that oceans aren't next to mountains, well, let's think about how we did it in SAT. We said that a region next to the ocean must be either forest or ocean. And we'll do something similar in our finite choice logic program, where we can say, well, like every rule in a datalog-like language, it forces the conclusion to apply if the premises apply. So this will make it the case that ocean-adjacent regions can't have mountains.
Okay, I haven't seen functional dependencies used that way before.
Right. So nonetheless, these four rules represent this possibility space we wanted of tile grids where oceans aren't next to mountains, and it correctly represents reachability from the starting location without the unjustified inferences.
That's pretty cool, but how do you precisely define the meaning of one of these finite choice logic programs? I mean, in SAT, it's pretty simple. Any assignment of true or false to propositions that makes the formula true is a valid meaning. For that matter, how does datalog define the meaning of a program?
Well, it's not that simple, but I'd still say it's pretty straightforward. So in datalog, everything that we're doing is in terms of monotonic functions that grow our database, the set of facts that we're gathering. So every rule is a function that can grow the database. If the premises are satisfied, then we can add the conclusion. For example, the transitive reachability rule is a function taking a database with a couple of facts. Two regions are next to each other, one's forest, the other is reachable, and outputting a database that also contains the fact that the other one is reachable. Informally, the meaning of a datalog program is just run the rules until you can't run the rules anymore. But formally, there's a pretty well understood recipe. Once you explain what one rule does, you join the result of all of the rules together. This is a function from databases to databases called immediate consequence. Then you need to show that the immediate consequence function is monotonic under set inclusion. Because sets ordered in this way are a complete lattice, the Kanaster-Tarski theorem gives us a least fixed point. And that least fixed point is the meaning of the datalog program. But in this case, a rule with choices seems like it creates a whole set of possible successor databases. So I don't know what it means to iterate this to a fixed point. The domain and the codomain aren't even the same thing.
Right. Yeah, so this is where things get fun. So you're on the right track with observing that applying a rule can be thought of as a function from one database to a set of databases. And in fact, there are actually sets of mutually incompatible databases, which means that any two databases will always disagree on at least one of their attributes. And this structure is something important for our definition in our semantics. We call it a choice set. And with this, equipped with this mathematical definition, we can actually follow more or less the same recipe that datalog uses. We'll just need one extra step. OK, so adapting this recipe. First, we're going to interpret each rule in a finite choice logic program as a function from a database to a set of databases, a choice set. Then we'll join the output of all rules using an appropriate definition of join. And that will produce our immediate consequence operator from a database to a choice set. And then the one extra step we need is just to lift that immediate consequence operator to be a function on choice sets so that we have the domain and codomain as the same. And once we do that, we need to show that this immediate consequence operator is monotonic. Observe we have a complete lattice. And the least fixed point of this immediate consequence function is the meaning of a finite choice logic program.
OK, so I recognize the pattern here, but I have questions.
That's understandable. So all of the gory details, of course, are in the paper. But maybe just to give you a flavor of it, I'll explain a key piece here, the ordering that makes choice sets into a complete lattice.
OK, so in datalog, we gain information and we grow our database by adding new facts. How are you going to gain information and grow a choice set?
Great question. So there's three ways. So there's the datalog way, in which it's possible for a database to have more information than another database by virtue of being a superset. And if we embed those databases in otherwise similar choice sets, then we can say we're also adding information to the choice set. So another way to think of this is that we replace one database in the smaller choice set with a single successor database in the larger. The second way we can learn information is by splitting into multiple possibilities. So when we freely choose a terrain type for a region, we are adding information by replacing a single database with multiple mutually incompatible successors. And then finally, we can actually gain information by removing a database. So if it violates a constraint, say by putting mountains next to oceans, then you can learn more information by removing that database. In other words, you can replace the database with 0 successors. If we put all these together into a formal definition, we get something with a kind of contravariant flavor to it. So a choice set C1 is less than the choice set C2 if for every database in the greater choice set, there is some smaller database in the lesser choice set C1. If any of you are fans and familiars of domain theory, this might look familiar to you as the Smith ordering on power domains, which is a common model of non-deterministic programming. So, in summary, the model of finite choice logic programming combines the mutually exclusive choices of SAT with the justified inferences and least fixed point semantics of datalog.
Great, and so all of this exists?
Yeah, actually, we have an implementation called DUSA, which you can access and try out at dusa.rocks. It's pretty good.
This is amazing. Surely nothing will ever go wrong. Pardon me.
I have more of a comment than a question.
Yes?
You see, answer set programming handles this combination of forced deduction and free choice that you've been describing. What's the connection?
So this is a great observation. Everyone, I'd like to introduce you to answer set programming, an old friend of mine who I've actually learned a lot from. And in fact, one of my original motivations was understanding ASP better. So let me give you at least a kind of a first answer here. So we have another kind of rule in the paper that we haven't talked about that permits a kind of default reasoning. And with that addition, we can actually translate all answer set programs into finite logic programs.
Oh. No offense. But why not just translate your finite choice logic programs into answer set programming? Are you giving us anything new?
Okay, fair question. So actually, yes. One of the big limitations of the standard stable model semantics for answer set programming is that it only gives meaning to ground programs, those without any logic variables in them. So in practice, this actually means that conventional ASP solvers require a separate grounding phase before they can even start solving, so they'll actually only be able to represent finite domains, and they can't handle possibility spaces with infinitely many solutions. So to illustrate this, let me give you the simplest possible example I can think of. At index 0 of this program, we will make a free choice between stop and continue. And then if we've made the choice to continue at index n, then at index n plus 1, we'll make that choice again. And so the meaning, according to the semantics that we've defined, contains infinitely many possibilities, one for each code natural number, and our DUSA implementation will actually enumerate these solutions productively. But given a similar answer set program, a conventional ASP solver would have to count to infinity before it would return solutions, so of course it won't. There has been work on something called lazy answer set programming that can handle these sorts of situations, but it's treated as an additional complication on top of answer set programming, whereas we found, kind of excitingly, when we started with this more direct denotational semantics, the meaning of infinite possibility spaces emerges naturally. And this stop and go example is, the simplest thing I could think of, but I'm excited about it in one case because I think it can actually scale to the task of, say, enumerating algebraic data types, which is something you can't easily do in ASP. So I hope that addresses some of your concerns, perhaps. Cool. Okay, so now, for real, in conclusion, finite choice logic programming unifies the strengths of datalog and Boolean satisfiability, generalizes answer set programming, and enjoys the least fixed point semantics in terms of these choice set structures. And we're excited about this approach to representing and exploring possibility spaces or sets of possible worlds defined by shared sets of rules that produce them. So I hope we give you a few reasons why finite choice logic programming might be worth learning more about. And if you'd like more math examples, experiment data, and so on, you can find it in the paper. If you prefer hand-drawn pictures and examples and puzzles, find me or Rob after the talk and ask for a zine. And that's it. Thanks very much.
So thank you for epic talk. So you said that is it working now? Is it working now?
Yes.
Okay. So you both datalog and stat-based things typically only work with grounded things, but you said ASP can handle ungrounded terms. So what's the connection to Prolog? Can you implement unification? Is it primitive?
So when you say can handle ungrounded, so ASP usually can't, SAT usually can't, datalog usually can in the sense that unless you wanted to add something to this, I maybe
Databases in datalog only contain ground facts, but
Right.
datalog is interpreted in terms of open rules.
Right.
So yeah, we don't have databases with unification, as you might expect from something like a formalization of Prolog.
Yes.
Have you tried? Can you implement unification into set?
We have not tried that.
Not something we've considered. Do you have a use case in mind for it, or is it other than just curiosity?
Yeah.
Is it-
Well, to try out implementing type inference.
Okay. Okay. Cool. Yeah.
More questions?
What's up? You good?
Okay, we have time for questions if anyone wants comments or questions.
There's no more questions. We can be done early. If you have one.
Okay.
No pressure.
How big is the implementation of this language?
That's a question for Rob.
Yeah, it's gosh, I don't know, I don't have a lines of code. The implementation, hilariously, is in JavaScript, and we do performance comparison against Klingo, which is in C, and sometimes we win. I've got graphs, but I'm not going to bother showing them. Yeah, so that's why the web implementation is directly running the thing. But it's a medium-sized web application, but remember, I've worked in web industry, so I may have a skewed view.
Again, fantastic talk. I think you probably win the conference. But could you call out just different problem spaces where you would love to see this applied? Like if you're working in map generation, you should pay attention, et cetera.
Yeah, I mean, for me, one of the kind of motivating, yeah, I'll let you go like that. One of the motivating applications for me was procedural generation in games. That's sort of the application area of origin for me. But but I'm also excited about basically any kind of domain where people are not looking for just a single satisfying solution, but many possibilities, and maybe not even where you care about a precise metric along which you're trying to find the best answer, but where there truly are many good answers that are different along reasonable axes of comparison. And these things come up all the time in program synthesis or property-based testing or other areas I've talked to people about. But, yeah, thanks.